Good day, and welcome to this video presentation done for the course ECNG 3022. We are Group 18, and our study was done on the problem statement: can a split ring resonator be used to harvest radio frequency energy from a nearby PCB transmission line? So, before we can get into this, we must discuss what is energy harvesting. And basically, this is the process by which ambient energy is captured and utilized from the environment. This energy can be captured from a number of sources, such as solar, thermoelectric, radio frequency, vibrations, or magnetic. These energy sources usually provide low amounts of power, so they are best suited for small applications, such as the powering of low-power sensors and small electronics. This project was focused on capturing energy from the electromagnetic wave created as a result of the passage of current through a PCB copper trace. This actual capture will be done using a split ring resonator. And what is a split ring resonator? This is an artificially created structure engineered with the intent of producing a particular response to incident EM waves. So how does this theoretically work? Here we have an image of a split ring resonator, and basically the split ring resonator cells are engineered such that they are smaller than 1/4 of the wavelength of the incident EM waves for which they are designed. This is done so that the refractive phenomenon of the EM waves dominates over the diffraction phenomenon of the waves propagating inside the split ring resonator itself. Due to this design, incident waves do not spread out among the SRR cells, but instead induce rotating currents within the concentric loops. These induced currents are produced by the magnetic flux generated by the EM waves. These currents generate further magnetic flux, which may affect the source EM wave itself, depending on the resonant properties of the structure. The gaps within the rings serve a dual purpose. They allow for resonance in the SRR cell at wavelengths greater than the dimensions of the cell, and they create large capacitances which decrease the resonant frequency of the SRR. So what does this mean for a particular situation? Well, without PCB copper trace, the SSR will be mounted in close proximity to it. As current flows through the copper trace, a magnetic field will be created around the wire, based on Ørsted's law. This results in the penetration of the split ring resonator by a magnetic flux, which is present due to the magnetic field created by the current. This magnetic flux induces rotating currents within the loop shape of the split ring resonator. This phenomenon is very similar to what happens within an RLC circuit, with similar increases to the induction and to the capacitive and inductive values. So then, creating our model and simulations were done using the COMSOL software. This screenshot here shows an image of our designed split ring resonator and the incident PCB transmission line. By varying different geometric parameters such as the gap width of the split ring resonator, or the trace width of the PCB transmission line, or the shape of the resonator. As you can see here, we have a circular split ring resonator structure and a square split ring resonator structure. The various performance or energy performance indices could be measured and compared. So using this software, it was seen that strong electric and magnetic fields were observed within the SRR gap itself, proving that it can be indeed used for harvesting energy. To measure the performance of this energy capture, S-parameter or scatter parameter plots were used to determine this. Now these S-parameter plots, the S parameter in particular used was the S11, which gives a measure of how much power is reflected from the SRR itself. Just as a brief recap of what the study showed, it can be seen that as gap width decreased, resonant frequency increased. As trace width increased, resonant frequency decreased. As the number of rings of the SRR increased, the frequency decreased. And it was observed that the circular split ring resonator structure displays superior performance as compared to the square split ring resonator. Here we just have a S parameter plot to show as an example. And the point at which S11 was a minimum corresponded to the frequency at which resonance occurred, which gave the point at which energy was a maximum. We also have here an example of a trace width versus resonant frequency graph to show one of our varied geometric parameters, and it can be seen that as trace width increased, resonant frequency decreased. So, just to discuss some of our recommendations, it can be seen that the results obtained were from a simulated environment, hence meaning for an actual SRR performance in energy capture, a prototype would have to be made and tested. And instead of a single SRR, a three-dimensional SRR array or a larger array could have been created to maximize energy harvesting. In conclusion, it can be seen that a split array resonator is indeed a feasible option for energy harvesting from a PCB transmission line. The results obtained from the simulations did match those of the previous literature done on the subject area. It was also concluded that additional testing was needed to determine the necessary geometric structure for maximum energy collection. This is some of our works cited, and I thank you for your time.